Okay. Okay. Hello, guys. So welcome to another session, weekday session of book club. So today we'll be going over the rest of the chapter that we have, the third chapter. We've been covering like uh, different sections. So let me share my screen. Again, I'll use the summary that is here, and we can also go over the notes if you have any notes added, or like I usually uh, have some notes on the book, like I have a Kindle version where I highlight that stuff, so I can go over that. So the target for today is the other indexes, other index structures. We went through the B trees last time, so other indexes. So I think here he talked about different kinds of yeah, indexing structures that we have. One is the straightforward key value indexes, where you have a key and there is a single key and index. And the other one is having secondary indexes, where I think it's like apart from having the primary indexes, you can also create a secondary index using the other values other than the primary index. This is available both in relational databases and in NoSQL databases as well. So, and one case is usually like the secondary indexes need not be unique, and they're not always unique. So, what they do is some of the secondary indexes are a combination of primary index, the primary key, and other value, which becomes a secondary index, which makes it a unique to do that, unique to make it an index. Um, So I think that's what they say both B trees and log structured indexes can use. So I believe B trees, when they say B trees, they're talking about relational databases, and log structured is like NoSQL. And the next one is storing the values within the index. So so there are so I think usually when we create an index, we have a reference to the actual value, not the value in the index, but there is a way to have the value also within the index, which makes it very fast, because you don't have a reference where you have to go and get the link, and that becomes a costly operation. But I think that's also very widely used. But I believe this is one way of optimization, storing the value. So that's what clustered index is, storing the index row directly within the index. Non-clustered is where uh, I think we have the link. Forgot actually. Non-clustered index store only the references. Store only the references is the non-clustered index. We have both in relational databases, from what I know. I don't know about NoSQL how they have this clustered versus non-clustered. Um, so if anybody has any experience there, because I know about the secondary indexes that I have used in NoSQL, not in production, but on a side project I have used that, and I know like we can set up this clustered and non-clustered indexes in relational databases. So if anybody have experiences setting up this clustered, non-clustered indexes in NoSQL, you can share it. Anyone? Okay, I would say maybe that's the topic that I don't know. How do you guys want to do it? Like, do we want to explore more on that? Clustered versus non-clustered indexes in NoSQL? Yeah, if anybody is interested, probably let's discuss on Discord. Okay. Okay. And one more index. I think most of these indexes, when author talked about those indexes, he did not talk a bit, no, he did not talk about them in detail. It was mostly like I think he was trying to introduce us to these indexes. Probably there will be more discussions in future, but I felt like there was not a lot of information there. he just talked about it and just gave an example. So I think that's what we are also going through, like just introducing ourselves to kind of indexes that are there.
Hello,
So,
Naga.
yep,
Hi, it's Pradosh. So I have a question here actually.
sure.
So while going over this topic in the book, right? So it talks about these other indexes, right? So we talk the clustered index, unclustered. Just to clarify, so the author probably means that these indexes are still in memory, right? Like in RAM, those indexes, because there's a mention of a heap file somewhere. So that would mean that it's probably a log structured file somewhere, where the actual data is stored. And he's just talking about indexes, like how to make reads faster, right? So is
That's
that,
my assumption always. Like all
yeah?
these indexes, I don't know if the complete index will be in memory, but
Mm-hmm.
uh, when these references are made, it is loaded into memory and then referenced. So the complete index may not be stored in the memory always.
I see. I see.
That's my understanding.
Yeah,
So, mm-hmm.
so my understanding is, so there are different types of indexes which are like in disk or in memory. So he's just talking about that what other various kind of indexes we have to store rather than index on just primary key. And but this but how you create the index, that depends. If you are creating an in-memory index, you
Mm-hmm.
will be creating that. If it's a B tree, then it will be a index on the disk. So it
Okay.
can be on anything, like your index could be in memory or on disk, whatever you want.
I see. I see. So probably the author is talking more about the way of creating indexes, but where you store is probably left, like it's up to us, whatever
Yeah,
information we've already gathered from.
yeah. So up till now in the book, he was talking about
Mm-hmm.
the about creating index on the primary key, where
Mm-hmm.
each value is unique. You have a primary key and you want to find the value. Now he's talking about what about the other indexes, like multiple value,
Mm-hmm.
searching for a key which could have multiple value, or searching for multiple columns in a table. So how are indexes created for them? So he's talking about that.
I see. I see. Okay. Thank you.
I think there is a section where there are like in-memory indexes section, like right after this. Yeah, yeah. There is a section I remember in this
You
chapter.
just passed it. It's about 12.
Okay. I think, yeah, yeah, I think they will get to that then.
Yeah, yeah, right there.
Yeah, keeping everything in memory. Yep, yep, yep. Okay. So that's with the clustered and non-clustered index. I think when you have like in a combination of both of these things, that's what he's calling as a covering index. Um, and then he also talked about like multi-column indexes, where it's like you create an index by combining multiple columns and create an index out of it. And he talked a little bit briefly about like how when you use multiple columns, how is the ordering used? Because when you use multiple columns, you also when you look for that particular key, the order needs to be consistent. I didn't talk in detail about it, but he talked about those multiple columns and like there is a way the ordering needs to be maintained, like how you select multiple columns. Um, so he talked about this multi-dimensional indexes also. Um, I think this is, he gave an example of where you have longitude and latitude as two different columns, but and you are asked to find like you need to query for a position, which is like a combination of latitude and longitude, right? So indexing based on this multi-dimensional values. That's also one kind of an indexing, but I think that's a very specific use case to use case indexing, I believe. If you have a specific use case, like you are always having this multi-dimensional queries, then I believe you would use that multi-dimensional indexing. We haven't did not give an example of like which, I don't think he gave an example of which databases support this multi-dimensional indexes. I haven't used any. I don't know uh, if there is any. I don't know if any RDBMS supports this multi-dimensional indexes. Any ideas, guys?
I thought it's very normal, right? That you create a index based on multiple columns. You say that my index is created based on column A and column B. Isn't it usual?
Um, Based on column A and column B.
Yeah, like my key is made up of combination of two columns, column A and B. So
Right.
that is just multi-dimension index, that you are not searching for just one column. You are searching with those two columns always. If your scenario is that you are always searching for latitude and longitude always in
Mhm.
your where clause, then you will create an index which is based on both those columns. So
Yeah, yeah. I don't know, like yeah, we talked about only two dimensions, but this could be like multiple dimensions also.
yeah.
Are you saying like once we create index based on this multiple values, that becomes a multi-dimensional index?
Yeah, it becomes a multi-dimension. Yeah. And then if you are searching in your database with those multiple columns together, then that will be indexed, so your searches will be faster. So basically you will create such index if most of your queries are based on the search for those multiple columns always.
Mm-hmm. I think I don't know like why
I
he
think
had to
that's
mention it.
how I understood too.
Okay. I don't know then why he had to mention it like in a different way. Like he said like multi-column indexes in a separate one and multi-dimensional indexes also. He mentioned this in a multi-dimensional index. The website needs to
I
select.
think multi-dimension and multi-column means same.
Mm-hmm.
So each column is a dimension, right?
Yeah, I think
Column is
here
a
he
dimension.
says multidimensional. Yeah, I think whatever is written over there, that just says that it's multi-column, right? Multidimensional indexes are a more general way of querying several columns at once, which is particularly important.
Mm-hmm. Mm. Okay, that makes sense. Then it's just like a indexing based on multiple columns.
Yeah, querying several columns at once. E-
Okay. Um, so what would be the so index is created as a uh, combination of both the values, or how would the index look like is what I'm thinking.
So he has proposed like multiple ways. So first is underlying indexing structure. It depends on you whether you are using a hash table or B tree or whatever. But
Mm-hmm.
using that existing thing, either you can like to uniquely identify a key, either you can concatenate those multiple columns together into a key and
Mm-hmm.
then store the index. Or he's saying is that you have separate indexes for each columns, and then when you are searching for a query, like first you find the key in that column, like for that column's key. So probably you will find multiple values, then you filter it with other columns key, and that's how you can get the results based
Okay.
on multiple columns.
Okay, so both of them are indexed. So when you query it, like it could be the database engine's way of how it can use it.
Yeah,
If
yeah,
we create, like two indexes for them, or we could create an combinational index
yeah,
with all these
exactly. Yeah.
values, right? Okay, okay, yep, makes sense. Okay, cool. So then I think the next one is a full text search. Here is the case where you don't have an exact key for search, but the search case would be like a subset of the key. And I think, uh, or I don't know how this is pronounced, Lucene, which is used by Elasticsearch and Elasticsearch cases, where it is indexed. I think he talked about indexing based on the uh, distances, distance of the key. So it's not like a key stored as is, but it's stored in a way like you can search based on the distances, is what it was talked about. He mentioned about try data structure is kind of a way that is used to do this kind of searches. So I think it kind of made sense when you use like a try data structure to search for like the subsets of the key. So anything else anybody wants to add on that?
Yeah, I mean, I just want to add this thing that, uh, so basically, when we are searching for something to make our search faster, we create indexes, right?
Mhm.
So like, this is my basic question to everyone. So you create index, right? Uh, like the basic index, very basic index you can create is a hash map, right? Where for every key you are hashing that at what memory location that value is present, right?
Right.
And generally hash tables have like big of one access. You go to that key and you find where the memory location is and get the value, right? So this is how you can quickly search for your data. So overall, this is one thing. Then why do we need these other kind of data structures like tries or like trees, b trees and all to create the indexes?
Correct. So I think like if it is only why do we need this try data structure?
Yeah, like why do we need b? So I'm saying that if you want to search for something, you create a hash map.
Right.
Hash map is big of one. You search for that key, you get the memory location of the value and you get the value. So why are we worried about creating b trees, tries and all those things?
So
Like,
Abhi, so the question basically comes down to what's your choice, right?
yeah,
So, like speaking from an interview perspective, let's say you are asked to design something. So so I think the way the author has put it is he has given us all the information, and he has also mentioned that LSM trees are typically are for read. Sorry, B trees are typically for read heavy applications, right? So typically when you're querying, so most things in the internet are mostly read heavy based, right? Twitter, Facebook and stuff. So when it comes down to designing an application such as Twitter or Facebook, you would probably have a trade-off. You would probably want to have a B tree where the reading is at max log of n, right? The depth of the tree. Whereas he also talked that, I think he also mentioned that because the write amplification is manageable for LSM trees, in case your application, you're designing an application, your use case is something that is write heavy, you would probably try to use a LSM tree, like a structured storage engine with SS tables. So I think it all boils down to like what's the use case. So if you have a write heavy or read heavy, based on these certain things, you can then do a trade-off and say, okay, do I have to go with LSM tree or do I have to go with B tree? Or maybe in this case, in fuzzy indexes, one of the use cases like Google search, right? So the user is typing some words, but those words may not be exact keys, but you want to give them like a search of, like a type ahead suggestion, right? So this is something for that thing you can probably use like a fuzzy index, right? So I think it all boils down to a use case. That's what I
so my
think.
question is, so yeah, so like you said b tree, you'll
Mm-hmm.
get login access time, right?
Mm-hmm.
Why not have a hash map on disk and you can search for those keys in big of one. So why
So
create a B3?
yeah, so again, so in the book specifically, the author has also mentioned that, in LSM keys, in the background, you would have a lot of segment files being made, compaction being done, and they're being reduced to smaller spaces. So reads might get affected because of compaction. Let's say a particular segment that is currently being compacted has the only key that you're looking for, right? For example, in SS tables, you do not have the exact keys, right? You have the boundaries of the keys, and then you like sparse index, right? And you index into the disk. So let's say a particular segment that your key resides in is being compacted now. So probably you cannot read until the compaction is done. Probably you have to wait. So this is what the author has mentioned, that in background, because of all these things that happen in LSM keys, your reads and writes can be affected. He did not go into detail as to how it is affected, but he did say that reads might be affected.
Okay,
That's what I took away.
probably, yeah, okay, probably
Mm-hmm.
see, this is my understanding. Uh, so what my understanding is, see,
Mm-hmm.
when we are searching for something that we know that this is the key and we want to get the value, hash map is great, big of
Mm-hmm.
one, right?
Mm-hmm.
But whenever your search query is something like this range that
Mm-hmm.
give me all the values between the key range from 1 to 10,
Mm-hmm.
greater than 1 and less than 10, right?
Mm-hmm.
Now
Mm-hmm.
see, what is the big problem we have with hash map? One big problem is that you don't know what keys how many number of keys you might have between 1 and 10. Like there could be
Mm-hmm.
1.1, 1.2, and
Mm-hmm.
so you don't know how many to iterate. So
Mm-hmm.
either you will iterate through the entire hash map, entire data, and see which key exists between 1 to 10, or not, and return the value, or you will create all the possibilities of values between 1 to 10 and search if those exist in the hash map. So, see, my
Mm-hmm.
understanding is, see, what he has been explaining in the book is that whenever you want to do range kind of queries,
Mm-hmm.
then the hash maps are not good. And so these tries, B trees, all these data structures, what they do is they keep your similar data together. Whatever data is has like similar keys, and it depends on your scenario. So like if your search query is always that you want to search for something with the same prefix, then you will create a data structure like try, where everything with the same prefix is
Mm-hmm.
stored together, so that if you're searching with the same prefix, then the try will give you immediately. If you are searching for range queries which are sorted in some way, then you
Mm-hmm.
can create B trees or things like that. So I
Yeah,
mean,
so I agree.
all
Yeah,
these
so
data structures, they
mm-hmm.
make your range queries efficient. And
Yeah,
I don't
exactly.
see a point like not using hash map if you don't have range queries, if you are just looking for key values. So yeah.
Yeah, so again, so this then boils down to a use case, right? Depending
Yeah,
on,
yeah.
say, let's say you're an application developer, based on your knowledge of how your application is supposed to behave under loads, write heavy, this heavy, do you need something like a range query? Then I think based on that, we can we can decide which database engine we should select, right? I think
But I think
that's.
this chapter we are trying to understand the what's happening under the hood, so that you can
Mhm.
use the right engine, right database for
Right.
your.
Yeah.
Exactly. So this author is basically giving us a bunch of ideas, and then as the reader, you are supposed to, I think, based on our application, the use case out of it, we are then supposed to select whether you want to using this or that or this. I think
Right.
that's.
I think that's the reason he
Mhm.
wanted us to understand how each one of this works. I
Exactly. Yeah.
think, yeah. Abhishek, thanks for that. Actually, I think we
Mhm.
have been reading through that, right? We started with why do we needed LSM trees, why do we need B trees, and different things. I think you kind of summed up those things, I believe, like how it started and came to.
Yeah. I mean, this was my understanding. Yeah.
Yep. That's true. Thanks for refreshing that. But I think for this fuzzy indexes, right, full text search, I thought it's not about like keeping it close, but it's also the way it is stored, right? It is also stored in such a way that it's the key is not the complete word, but the key is like the uh, the individual pieces of that word.
Yeah, I
Like
mean,
is close, like it's a misspelled word, right? So whatever is the closest match you have,
Hmm.
those are all the options that it can suggest.
yeah, I mean and I don't have a deep understanding of how these fuzzy indexes are made, but my uber understanding is that data structure, whatever data structure is, that data structure will help you search for those similar things in an easier way. Like taking a simple example of try, you keep your data in such a way that the all the keys with the same prefix you can easily search. So there would be something similar. And so like how they would be doing it by referencing the words which are similar. Maybe they would be referencing them with each other so that they're easy to find, or I don't know, some mechanism. But that's what they ultimately want to do, that whatever your search type is,
Mhm.
that data is easy to find in that database.
Okay, okay. So yeah, he mentioned that Lucene uses SS table like structure for storing these things.
Yeah,
So I thought like we don't even know what the prefixes are, right? So to search for, I thought the prefix is not even defined in the database, but everything is stored as an individual, uh, as individual keys as possible. If suppose like the search is based on a word like book, then I believe they have it stored like B as one index and OO as different is what I was thinking.
so see what is, I think what's happening with SS table is, remember SS table is the data structure where we keep the keys sorted, right? We keep the keys in sorted way.
Mhm.
So I think what would be happening with these fuzzy indexes is that this finite state automation would be given a query. It will be giving you what are the nearby terms for that query, what are the nearby valid terms in the dictionary. And then once you have those list of words, because your data is sorted, you can quickly search for those in that SS table.
Mm, okay.
Probably this, but I don't have any idea. I'm just guessing.
Yeah, yeah. I think he mentioned about it, but he did not even.
Yeah.
What he says is like Lucene uses as a stable like structure for their term dictionary.
Mm.
Yeah, and next memory. Yeah, he did talk about like finite state automation over the characters in the keys, similar to try. So okay, I believe like probably he's introducing to that index. I think we have a good sense of it now. Okay. Okay, moving on. So he talked about uh, this indexes keeping everything in the memory. So this is one way of storing it. Here, when he says everything in the memory, I'm assuming like the complete indexes are stored in the memory rather than the like we were talking earlier, like that is defined differently, right? Indexes could be on the disk or in the memory.
Yeah.
I, yeah, so here I believe he's talking about all the complete index is stored in the memory. So this is
Yeah.
one way of, I think there are some latest, uh, I don't know if we should call databases, but there are in-memory solutions that are available for storing all the indexes. So um, thing, things that he talk about here are like because RAM is getting cheaper and cheaper, they want to store in memory, and he also talked about like the biggest challenge of keeping in memory is like the data is lost once the power is gone. So he talked about like how RAMs can be powered by batteries and all, and he also briefly talked about um, uh, it's like the advantage of having everything. I think he talked about a couple of things when he talked about in memory. He talked about when you say everything is in memory, it may not be always possible to keep everything in memory, but it will still maintain major chunk of it in the memory, and then swap as needed into the memory in an optimized way. So that's one thing he talked about in memory challenges. And also he talked about things like operating system also does this by default. It's not like it also maintains a cache of like what is the least recently used, last recently used into the memory. So that's already there. Then what is the advantage you're getting by having a complete in-memory solution, which also needs to swap as needed. So I think he talked about like what is stored by the operating system is not optimized to what the application needs, because it's like for operating system it's like a page, right? So this was the last page that was read, so it will swap that page by page. But this in-memory solution is like, okay, this is the record that I have read last, so I'll put that in memory when I swap or when I bring back. So those are a couple of things he talked about here, I believe.
So Naga, I have a small question. So you said that. So my understanding is that in this example, right, in memory databases, you're actually storing the entire data set in memory, because the premise is that RAM is becoming very cheap. You may be able to do partitioning, so you're not storing your data in just one machine. You're probably partitioning your data across many clusters. So it makes sense to have the entire data set. Maybe you've sharded something in the memory. So I don't think that he's talking about just putting the index in the memory, because I thought I heard that you said he's probably talking about the index. Maybe I heard it wrong, but
No,
he's
no.
probably saying the entire data is in the memory, right?
I thought it is indexes because we are talking about indexes here. I didn't.
I think it's like it could be both, like, and depends on the implementation. Somewhere, yeah,
He talked
data and
about
index
data
are
set.
both in memory.
No, but Abhi, but the example here, right? Memcached from Facebook, right? So that specifically stores the entire information, because if you're just storing the index, you're anyways doing a IO to the disk. So there is no perceived read like performance, like it is degrading your performance, right? So if you store the entire information in memory, at least that's what Memcached does. It stores the entire thing in memory. So this Memcached is like a key value store. You say you do get something, it will give you from the cache itself,
Mhm.
right? Only if there's a cache miss, then only it'll ask and go to the actual DB, like actual spinning disk, get the information out and put it in the cache so that the next reader can hit the cache.
Mhm.
Yeah,
So I think
I
here
think
they are maintaining, they're probably, so that's why it is said that it's an in-memory database, not an index, I think.
yeah, I think you're right. Yeah, yeah,
Even here it says, right, many data sets are simply not that big. So
Okay,
it's
yeah,
quite feasible to keep them.
okay,
yeah.
okay. Yeah, I just wanted to clarify that.
Memory
Okay, thanks.
database restarted, it needs to reload its state. So either from disk or over the network. Okay. Okay. So
So I had a question with this in memory, and I couldn't understand what exactly he means by the second last point. Like this, they can be faster because they can avoid the overheads of encoding in memory data structure in a form that can be written to disk. Because like at one point he's saying, just because RAM is cheaper, it doesn't mean like like disk-based storage is not fast enough. With help of caching, it's possible. It's just that with in-memory data structure, because of the way this the in-memory data structure, how RAM handles it versus how disk handles it, it's different. I was just trying to understand what exactly he means by that.
yeah, yeah. So I think what he's talking about is like when operating system does it, it doesn't have an idea of like what is the record and what is the half record versus what is the full record, right? For it to know like what to cache or what to pull it back. Because operating system doesn't know what your data is. It only knows like, okay, this is the memory which is in the cache, and now I need to get back some data back into the cache. But in
So
case of this kind of caches, we know like, okay, this record was last read, so I pull that record here, and if not, if the if that's already there in the cache or not, right?
So Naga, so just a quick addendum here. So I think someone asked, right, what the third point. So the third point, I think, like if you just read that text, it is not very clear. But if you see that they can be faster, so this kind of reminds me of this the way that memcached is actually implemented. So what happens is that most of the time, your application needs information that is encoded in certain format. It doesn't want to get raw information from the DB and then try to churn it, right? So when you put a memcached in front of the DB, what usually happens is that if there is a cache miss in the memcached, it goes and collects information from the DB, processes it based on whatever it requests, and then stores that partially processed information into the cache in the memcached. So that next time if another client, like same application, wants to use the data, it is faster for them because the data is already partially processed and stored in the cache. So is that something to do with when he says they can be faster? Is it, I mean, faster
Yeah, I
from an
think
application point of view?
the point that I am missing is like, or the way I took it is, or the thing that I didn't understand is like, why is he saying that they can avoid the overheads of encoding in-memory data structure in a form that can be returned to disk? So what kind of encoding, like, why is it different in the way the data is stored in RAM versus the data that is stored in disk? That is what I was trying to get clarity on.
Yeah, he mentioned about that in page 135, this exact point actually. So I felt like who is handling that data, right? Putting the data back into disk and putting back into the cache. So in case of RAM, operating system does that, right? And in case of this memory, like it's a known data structure, and we know like what needs to be cached and what needs to be brought from the disk. And
So
if it is
yeah,
operating system, it has to encode it back. And in this case, in our memcache case, we know that this record to record, there is a mapping between record to record, right? There's no encoding and decoding.
I think it's about the underlying hardware difference. So in RAM, like you have memory address of those bytes, and then you are storing data in the in those bytes, and everything you can, each memory location you can access very fast. Like your hardware is, the RAM hardware is connected in such a way that those accesses are very fast. Whereas hard disk is divided into sectors. So you have those fixed size sectors, and you are storing the data in sectors. So let's say if you have a in-memory data structure, let's say some tree which has a huge height. If you are storing that as it is on disk, like I don't know like how you will store it, but also it will be very inefficient, because if it is a 50 level tree, then you are specifying the memory location that at this sector I'm storing this node. Then at a I will add a pointer, and at this sector I'm storing another node. So probably you are wasting the space of the sectors because you're just storing that one value. And then also, if your height is big, then you are making references to other sectors. And on a hard disk, the seeks between the sectors is not very fast. So because of this, like you would need to encode your tree in a data structure which is efficiently stored on the disk. So an example is that for tree, you create a B tree, and B tree is such data structure where you reduce the number of levels and you store everything in one sector as much as you can store in one sector, and then store it in disk. So this is how you have encoded. Similarly, for other data structures which are in memory, you would need to do some mapping, which will be so which is something that you would have to work on. So that is what he's saying, that that's why, like, in memory data structures, like, you don't have to worry about this encoding.
Hmm.
Okay, yeah, that makes sense.
Yeah, that's right. I I think he had a link to one of the papers on it actually. So from the
Yeah,
page.
I think the point or the reference number that he says is 44, and for that, it's like an OLTP topic for that reference. So I wasn't sure what's going on there.
Yeah, I was looking through it. I think he had like buffer manager and all. So I'm assuming he covered it here. Yes.
Yeah, OLTP through the, yeah, I think that's what you have open, right?
Yeah, yeah, I opened that link actually. So,
Yeah.
okay.
Okay. All right. Thank you.
Yep, yep. Okay. Cool. So with that, I think indexes and keeping in memory is good. Um, After that, I think he introduced us to like OLAP kind of structures where the requirement is more about I think like OLAP is more about like for reporting and reporting stuff, right? So um, I think he online transactions OLAP versus I thought he yeah, I think he gave couple of differences between these two kinds of systems, like how it matters. Okay, data warehousing, the divergence between this and all. Okay, let me go through my notes because I don't know. This is not covering all the points I saw, I believe. So, okay. Hmm. Okay. I think basically like he talked about like two kinds of systems where we have like this uh, uh, transactional based queries and like reporting based kind of queries. So these are two different kinds of systems. So one and like two have different kinds of purposes, and we use something called ETL to actually load into this OLAP kind of systems and run queries on them for kind of reporting purposes. I think in the next sections he talked about like how do we make them more optimized. But I think in this section that's what he introduced us to, and I think stars and snowflakes are the two kinds of models. How this data is stored in uh, stored for OLAP. Um, he gave a couple of examples. I think he gave one example where a single fact table is maintained, and then it has like very lightweighted links to other tables which are used to join. But the most of the data is held in these fact tables uh, to answer questions, different kinds of questions needed for the reporting structures. I felt Snowflake schema is also similar, um, but I think he added uh, yeah, column oriented is different. So it's broken down into sub dimensions. I believe Snowflake is more about adding more dimensions to what are there in star schema. I did not get like the exact difference between star schema
I think
versus
Snowflake is more normalized.
more
So
normal. Mhm. Because in star schema, he said like there is one fact table and which contains most of the data, and then there will be references to other tables like foreign keys, like multiple foreign keys in it with multiple. So you're saying like Snowflake will have more of those, or
yeah, he kind of expanded more on that. So
Mhm. Okay, okay. So okay, I'm just looking at any notes I have. Okay, cool. Then he talked about like column oriented storage. So when we started with this, it did not make sense for me. Like what does it mean? What does it what does he mean by column oriented storages? But then when I read through it, like I read through it once, and then I felt like most of the reporting queries are like when you look at the tables that we have in relational databases, we say like um, we say we have like multiple columns, but when you for most of the reporting things, what we need is like it's usually like one column. It's uh, like if there is a uh, there is a table like what are the orders that are taken between this time. So we only need like the orders that are taken this time. So I felt like there's only like in most of this reporting, there's only like column data that needs to be queried. So this when we want to support OLAP systems, the emphasis is more on this optimizing on these columns. Um, so that's why I felt like the column oriented storage is well suited for this OLAP kind of systems. Does it make sense, guys, or any other thoughts on it? I think he talked a little bit more about like how they can optimize this column oriented storages and like how the compression is done and all this stuff. But in general, I felt that's the difference when he talked about like column oriented storage, because the queries that are written are not like the responses are not like a specific row, but it's a combination of rows, and a very specific column is of interest for this kind of queries. Any other thoughts, guys, on that?
Has anyone used any OLAP database, or has anyone any experience?
Yep, that's a good question. So in general, like OLAP would be like the data warehousing solution. So
Yeah.
what would be an example? You can look up OLAP systems. OLAP systems examples. Huh. 10 best Explain. I haven't even heard about it. IBM Cognos. Cognos is, I think, a bit famous one, right? IBM Cognos software. Palo, Pachiclin, IQ, Pentaho, Mondrain. Oracle obviously should have something. Girox. Okay, I think the only thing I heard is Cognos, but I don't know if that is in sense of IBM. Mm. That's what I heard about. Any yeah, looks like no one has experience on those.
Yeah, I have experience, but I have used like internal, like my company's internal OLAP databases. But this makes a lot of sense to me, like because I have used these stuff. So like one basic thing is like whenever you are doing any transactional kind of query, then you are looking for a particular record. Like let's say I am a user logged in, then my database would be fetching those rows which are related to me. So my database will be searching for that particular records, right? Whereas in OLAP, what you're generally doing is like to the leadership or to the analytics team, you are providing the overall data that how your product is doing, what are the most selling products. So basically your queries in OLAP would be something like who are my like what is my total sales in this month, how many customers have brought more than these many orders. So things like that, where you're not looking for a particular record, where not you're not looking for that particular individual, you're looking for some aggregation that how many how many kind of queries rather than that particular query. So this is the main difference, right, which he has mentioned in that first paragraph, that you are looking for those aggregation.
Yep.
The second thing is that in these databases you are so you are storing everything. So basically each row will have lots of columns, lot of data, because you want to store every fact about the user, that what was its date and time when he placed the order, uh, what was his machine name, his session id, because you, for audit purpose or anything, you might need any information. So at that time you are storing that fact which has lot of columns, right? But generally for your these queries where you are doing these kind of queries, that how many customers, how many, you would need only those 4 or 5 columns. You, most of the time that data is just stored for those audit, or maybe in future you might use it, but mostly you are dealing with those 4 or 5 columns. So
Mhm.
that's why he has mentioned. So and like I have seen this a lot, like I can relate to it. It happens that your database has so many columns, but you are mostly dealing with 4 or 5 columns.
Yeah.
So yeah, so and that's why storing it column wise makes a lot of sense, because whatever value, and generally you will see that for a column you might have lot of repeated values, right? A
Yeah.
particular column will have same value. So storing it column wise helps you in this way, that you can compress those same values and you can store the data in lesser space.
Yeah.
So this is why, like, he
Yeah.
has mentioned about this column oriented storage.
Yeah. 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 That's what I found. Uh, that was my takeaway. Like the when you look at, depending on the kind of a query, what makes more sense. Here he talked about like every time when you query, the response is a column that comes out. So that's the reason the column oriented was necessary for OLAP. Yeah, I think the compression you talked about is like, that is true, right? I mean, like most of the times when you are interested in all the columns, only that column, and a lot of times you see like the values in the columns actually repeat. So when you look at the rows, all the rows as an entity are unique, but in the columns they are all unique. I think he talked about like how to store them using bit mask, when you have like a lot of repeated columns, and save a lot of space on it, and make the queries faster. He talked about that in the compression. Um, I think he also talked about vectorized processing. They can be designed to operate on such chunks and compressed column directly. I think that's what he meant, like uh, using this bit masking to actually store and retrieve them. Um, at a time, different queries benefits different sort of orders. I believe we kind of covered in the discussion like how this column-oriented storage is actually helping. Aggregation. Okay. I think he kind of talked about data cubes and materialized views. Um, I think most people would have used the views in the RDBMS system, right? Where you have a query behind it, and whenever you try to query for the view, that query is that query behind is run, and this view is created for you. Those he calls as the standard view, and materialized views are like uh, I think from what I understood, it's it's a bit more advanced rather than like a simple query, and also they contain information more than in a view. It's usually like whatever the data that you have in the table, that's what is represented in the standard views. But in this materialized view, actually you, out of the data that you are querying, you actually create new data points and represent that in the materialized view. I think that's the major difference between the regular views that you have in your relational database versus when you talk about materialized view. So it also includes some analysis of the data that is used and create a different kind of view. The backend data is same, but you actually analyze the data and create a view for it. So anything else that anybody wants to add on that? I think we are almost out of time, but I believe we can finish this up. Okay, so anybody wants to talk about data cubes? I think I read about it, but I'm not too quite sure about that. So any thoughts on the data cubes? Okay, let me see if I have notes on the data cubes. I read about it, but I kind of forgot. Mm. Okay, guys, I'll not hold you guys on that, but materialized data cube, certain queries become much faster because they effectively be pre-populated. I think data cubes are created using the materialized views. So from what I have highlighted my notes, if you guys have any other thoughts, then we can talk about it. But otherwise, I think that's what it is. Any other questions, guys? Any other questions or anything that people want to discuss on that? Do we have people? Okay, guys. So then that's all I think we have in the chapter 3. We have summary points, but if you guys want to talk on anything specific based on what we have been talking, we can spend some time. But otherwise, like we are already little over the time, so I'll let people decide. I can stay back to keep this running, but let me know if there is anything that people wanted to add as a summary of what we have been discussing, or do you guys want to like go over quickly to see like review the complete chapter 3?
Are you talking now or?
Oh no, I'm just telling, like I think we are almost done with we are done with the chapter 3. I'm just wondering if anybody wants to add anything or like
Yeah.
want to quickly summarize or anything that they wanted to discuss on the overall chapter. Okay, looks like nothing, so I'll stop recording.
So yeah, I have a question regarding next session. You can stop the recording.